Okay, this is Statman. Welcome to AP Stats Chapter 5, Day 3. We're talking about some basic probability, independence, that word right there, independence, and mutually exclusive events. Mutually exclusive means, can also be called disjoint. Okay, so back in geometry, you had an if and only if statement. Independence is one of those. If and only if one event does not influence or change the probability of the other, do you have independence? Here is the math formula, which I'm squaring right now. Okay. So it's the probability of A times B equals the intersection. This intersection, this symbol right here means intersection. Okay. And that will be both of them multiplied combined. If the events are mutually exclusive, now be careful with the term mutually exclusive. It means can't happen at the same time. Disjoint is another word, another one. If you say not mutually exclusive, that's a double negative. Not mutually exclusive would mean not happen at the same time, meaning it can happen at the same time. So once again, mutually exclusive can't happen at the same time. Not mutually exclusive means it can happen at the same time. And if two events are mutually exclusive, that means their intersection right there is zero. It never happens. In other words, their Venn diagrams do not cross. Okay, so there's your start with that. Let's get into how these things work. Okay, so first, let's just do some simple checking if events are independent or dependent. Now, independent means there's no influence. Dependent means that there is some influence. Now, it might be very, very little, or it might be a lot of influence. We don't get into the levels of influence until later on in the course when you start studying the chi-square tests for independence. You get into those things. That's a little bit later on. But for right now, if things are not perfectly independent, we call them dependent, even if there's very little influence. Okay, just for some clarification. All right. 1A, if you roll a pair of dice and get an even sum, then getting an odd sum, dice have no memory. They have nothing to do with each other. Those are independent events, okay? Now, in 1B, randomly selecting one student from this class to move to 0 period, then selecting one to move from period 7. Well, your chances are going to increase that you're going to move to period 7 after one kids get removed, because that's a non-replacement issue. So that's dependent. Non-replacement is dependent. The NFL draft is the classic dependent one. Like, who are you going to pick with the 7th pick in the first round? Well, it depends. Obviously, it depends on who has selected it, who has been selected in front of me. A lot of you guys are in fantasy football, so you know the draft picks depend on who is available. Okay, now, this is a quick math check. Probability of A is 2/5 and B is 1/4, and their intersection is 2/15. So what you're going to do is you're going to multiply 2/5 times 1/4, and you're going to see if that equals 2/15. And if you do the math, 2/5 times 1/4 is 2/20. So they are not equal. So therefore, there is some dependence. And if there's any dependence at all, we call it dependent. Okay. Here's another one. Okay. 0.27. Let's see. 0.27 times 1/5. Okay. Does that equal 1/20 or 0.05? It doesn't. You can check the math behind me, but 1/20th is 0.05. 0.27 times 1/5 or 0.2 is not 0.05. It is not equal. So therefore, those are dependent. Now here's one that's independent. Okay. 0.82 times 0.15. That does equal 0.123. And because their product is the individual numbers multiplied together, then those are independent events. Okay. A good example of independent events from the sports world is you got a football game in Minnesota going on between the Lions and the Vikings. And you got a game in the South going on between the New Orleans Saints and the Atlanta Falcons. Those two games have nothing to do with each other, especially if they're both going on at 1 o'clock Eastern. So it's not like if one team's winning in the northern game, it affects the southern game. It has no effect on it. They're independent events. Okay. All right. So there's independence. The big thing to remember about independence, and I'm going to write it real big up here, is independence has to do with multiplying. Okay. So if the product of two individual probabilities equals their joint probability, then you have independence. If not, then it doesn't. Okay. Okay, so next part. Mutually exclusive or not? Mutually exclusive asks the question, can they happen at the same time? Okay. So can a coin land on heads and land on tails? Obviously, no, they can't. So those are mutually exclusive. Okay, question H. Can you be a US citizen and a Canadian citizen? You can. Those can happen at the same time. So that's where you get the double negative, not mutually exclusive. That means they can happen at the same time. Okay. Now, can you get a 3 or higher on a 6-sided dice and an even number at the same time? You can. So let's make a Venn diagram of this. And if there is intersection at all, then they are not mutually exclusive. So a 6-sided die, a 3 or higher, is let's see here. It's a 4, a 5, or a 6, correct? And then an even number is a 2, 4, 6. So you can see that they overlap on two numbers, a 4 and a 6. If they overlap at all, they are not mutually exclusive, meaning they can happen at the same time. Okay. Now right here is some basic things you should know. Probabilities are between 0 and 1. 0 means never. 1 means always. So 0.9 is 90% chance is really high. 0.1, 10% chance is really low, etc. Okay. Now, all the individual probabilities within a data set have to add to 1. So that's something that has to add to 1, and you guys should know that. And then the complement, so if a chance of rain is 25%, the chance of not rain is 75%. Okay? Now, and the word and means multiply, and the word or, you're going to use the addition rule, which we'll introduce pretty soon. But or means plus, and means multiply. Okay, those are some simple vocabulary words, all right? Okay, so let's go down to the next part. This is your classic bag of marbles. This is the kind of stuff you may have seen way back in, 7th grade or something, this kind of stuff right here, okay? These are pretty easy to go through by yourself. So we got 20 marbles in a bag. Find the probability of a blue marble, then a blue marble with replacement. No problem. So blue is 8. A blue is 7/20. So this one is 7/20. If you put it back times 7/20. Sorry for my terrible handwriting there. And it ends up being this 49 over 400. No problem there at all. That's easy. Okay. A blue, then a red without replacement. So a blue, then a red without replacement. So a blue marble. So I'm on this one right here. A blue marble will be 7 out of 20. And then a red times a red marble would be 5 out of 19 because you didn't replace it, took the blue marble and kept it out. And that equals, of course, 35 over 380. Okay. Okay. The next one, a yellow marble, then a red with replacement. So a yellow marble is going to be 8 out of 20 times, and then a red marble. So if you put the yellow in the back, you still have 20 that you're choosing from. Then a red, it's going to be 5. Okay. So it ends up being 40 out of 400. No problem. Okay. And then the last one, we got quite a bit here to do. A blue, then a red, then a red without replacement. Okay, let me write this out. A blue first. Blue marble will be 7 out of 20 times, and then a red. There are 5 reds, 5 out of 19. Remember, no replacement. Times, and then another red. So because you got a red the first time, there's only 4 left. So 4 out of 18. Sorry, 18. So you got 20, 19, 18 in the denominator. In the numerator, 754, and that's going to equal this. Okay. All right. Question 2B. This is a table. Probability can happen in tables too. This isn't real hard to do, but if you've never seen it, you can easily make a mistake. So based on the table provided, find the probability of randomly selecting a girl. So a girl is going to be 41 out of 80 right there, okay? 41 out of 80. You're using the marginal total divided by the table total. Then a sophomore will be 25 out of 80, once again using a marginal total and dividing by a table total, okay? A junior boy, so this is a junior and a boy, right? So a junior 11th grade boy. So that's going to be 16 out of 80. That's one of the cells. When you see and in a table, a junior boy is basically and, a junior and a boy. That means find the cell that has both qualities of the two parts, a junior and a boy. Okay. And the next one is a non-freshman girl. So we got girl that's a non-freshman. That's these two added up, a non-freshman girl. So that's those two added up divided by 80. Okay. As simple as those things are, they do happen sometimes on the AP test, and you got to get them right because it's pretty easy. Okay, so let's go to C. Okay. So on C, 60% of this is like an election. So you got Prop A, let's say Proposition A is like a tax thing, lowering some taxes. And then Prop B is maybe some funding for schools, and that most people like to help fund schools. So most people don't like taxes. So let's say 60% of the voters approved Prop A and 90% Prop B. Find the probability of voters who, now I'm making an assumption here, which is not written. Assume that in question 2C, assuming this question, that Prop A and Prop B, when people vote for it, it's independent. We're going to assume that. That may be a bad assumption because people often vote against, spending more money or for it as a block. But let's just pretend that they're independent. So you can walk through this very easily. Voted for both A and B, no problem. If they're independent, you can multiply 0.6 times 0.9, no problem. Voted for A but against B. Notice on this one, the complement is used for 90%. I'll put a little arrow there. It's 1%, okay? And then 3, voted against both A and B. So you got to do the complement of both of them, 0.4 times 0.1, okay? And again, that's assuming independence. Okay, so, all right, next one, D. Okay, we got with and without replacement here. You got cards. You got to know cards a little bit. If you don't know, there are 52 cards in a deck, and there are 4 cards of each kind of a 2 through a king or an ace. Okay, so a king and then an ace without replacement. So look right here. If you get a king, there's a 1/13th chance, which is 4 out of 52. Then if you don't replace it, the chances of you getting an ace is slightly higher, 4 out of 51. But getting that is not real likely. It's less than 1%, but there it is, okay? The next one is 1 red card and 1 black card. Now, if you don't know, there are 26 reds, 26 blacks, and without replacement again. So getting a red card is 50%, 26 out of 52. If you don't put that red card back, the chances of you getting a black card is slightly increased to 26 out of 51. So the answer is almost 25%, half times a half, but not quite because of the non-replacement. Okay. And then a queen and then a spade with replacement. A queen, there are 4 cards that are queens out of 52. That's 1/13th there. If you put it back in the deck and then shuffle again, the chance of you getting a spade, if you don't know, there are 13 spades, 1/4 of the deck. So this is actually 1/13th times 1/4, and it ends up being 1 out of 52. Okay. All right. We got 2 more to do. Let's do E and F here. So let's do E. A single 6-sided die. You guys all know what a die is. What are the chances you get all 3s? Well, all 3s is going to be 1/6 of the time. Okay, multiplied to the 3rd power. 1/6 times 1/6 times 1/6. And remember, you got natural replacement with the die. You can't like do non-replacement because it's a die. It just gets rolled again. Okay. Then all 3 are odds, and there are 3 odds, 1, 3, and 5. That's half of the rolls. So that's a half times a half times a half. Okay, that's easy. Okay. No 5s. Now, I really want to point out these 2 right here. These are the ones that are hard, or at least you need to learn them. No 5s. So no 5s would be, you got to figure out the chances of you not getting a 5, which is the complement of getting a 5. Getting a 5 is 1/6. So there are 5 non-5s, okay, which is 1, 2, 3, and 6. Okay, 1, 2, 3, 4, and 6. Can't count. So you're going to multiply those 3 together, and you're going to get this. Okay. I think it's kind of an interesting number. If you were to roll 3 dice, it's almost 50-50 that one will be a 5. It's kind of weird. You know, it's pretty high. It's a lot higher than you think. People don't think of those things. And then at least 1 odd. At least 1 odd. Now, at least 1, please memorize this. At least 1 is 1 minus none. So odds are 50%. So the evens are 50% as well. So these 3 numbers is actually the probability of getting an even number. 1 minus all evens will give you the probability of at least 1 odd. Okay? And that's going to show up a lot more in day 4 of our lesson, the at least 1 stuff. So if you don't pick it up there, it's going to show up a lot in day 4. Last one, 2 dice rolled together. Now, 2 dice rolled together. First of all, you probably need to, you got to go back to day, let's see here, day 2 of our notes, maybe. There we go. You got to go back to day 2 of the notes. And right here, we have all of these, the combinations for a dice. When you roll 2 dice, the most common roll is a 7. And it's real uncommon to get a 2 or a 12. So these have to be on your mind or have them written out when we get to that question. So refer back to day 2 to get those notes, okay? So when we are here on this, let's see here. There we go. Okay, 2 dice. Here we go. A number larger than 4. Okay. A number larger than 4. Okay. A number larger than 4. You know what? I just realized I showed you the 2 dice rolled together for no reason. Just forget that part. Okay. Now we got 2 dice. One is 1 through 6, and one is A through F. Oh man, come on. Okay. Similar idea. There's 36 combinations. Okay. So a number larger than 4. If you roll these together, larger than 4 would be a 5 or a 6. This is a lot easier than I thought. 1/3. A consonant. I'm not even sure what a consonant is. Is that A? Is that B? C, D, and F? Yeah, that's it. So that's 4 of the 6. Okay. Sorry that I led you down the wrong path with them. Well, at least I referred you to day 2. Okay. An even and a vowel. Okay. What are the chances of getting an even number? There's a 50% chance of that on the first die. And remember, these are independent events. So you can multiply them because these dice have nothing to do with each other. Okay. So an even number is let's see here, 2, 4, 6. There's 3 of them, 3 out of 6. And then a vowel. A vowel is going to be A and E. So it's going to be a half times 2 6, which is 1/6. Okay. Now this is cool. An even or a vowel. Ooh, this is a really, really cool problem to do. Okay. An even number or a vowel. Okay. Now there are 36 rolls. Okay. So again, I guess if you referred back to that other thing in chapter and day 2, it kind of makes sense. But in an even number, there's 18 combinations that'll be an even number when you roll the 2 dice. Okay. So that's right there. A vowel will be 12 of them. However, you've double counted 6 of them. You've been counted twice. Okay. So this is an example of a situation that is not mutually exclusive. Okay. So on this problem, let's go ahead and draw this thing out. Let me take the time to draw this. Okay. So this will take just a second here. And this is now going to look just like chapter 2. So we got, so you got 1, let's see here. Oops. So we got 1A, 2A, 3A, 4A, 5A, 6A, 2B, I'm sorry, 2A, 2B, 2C, 2D, 2E, 2F. I'm doing sample space on this, which I talked about in a previous lesson. If you don't know what to do, do sample space. 3A, 3B, 3C, 3D, 3E, 3F, 4A, 4B, 4C, 4D, 4E, 4F, 5A, 5B, 5C, 5D, 5E, 5F, 6A, 6B, 6C, 6D, 6E, 6F. There's your 36 rolls. Okay. So let me try to change. Let's see here. Go for my highlighter here. Okay. Okay. So, an even number. So an even number is going to be 2, all the 2s. There's 6 of those. all the 4s of the 36 combinations here, and all the 6s. 2, 4, 6. So that's 18. And that's where you get that 18 right there. Okay. Or a vowel. A vowel is an A or an E, correct? So all of these, there are 6 of those, and E's right here. And there are 6 of those. Oops. I'll edit them right there. We go. All the E's. So that's where you get 6, 12 of those. So 18 and 12 is 30. There are 30 that are even or a vowel, but we double counted. Now we double counted. We double counted this one right here. I'm sorry, this one right here. 2A, 4A, 6A, and then the 4A, what, and all the E's. I'm sorry, and all the E's. We double counted that and all the E's down here. 1E, 2E, et cetera, et cetera, et cetera. So we double counted 6 of them. Okay. So you have to subtract out where you double counted and divide by 36. This is going to happen a lot, this double counting concept. And it's going to pop up a lot, especially when you start getting the rules for addition. We're going to go over that pretty soon in another lesson. All right. That's it from here. Go get them, Stat Nation.